has been always a passion for me, but I never studied, never dedicated myself. I started just past year to get into it. 15, 20 years ago, I participated in research in neural networks, adaptive systems. But at that moment, the technology was different from now. I was creating my own neural networks. So I'm trying to catch up and learn everything I can do this.
Perfect. Thank you.
Hi, my name is Harish. I'm a grad student at Lofty. I study industrial engineering. So, like the past couple of months, I've been taking courses in machine learning, deep learning. So I know, like, I do your sessions, and I came for like first two initial talks.
Yeah.
And then I just followed up. That's it. Cool.
I remember it was also the barbecue, right? The initial idea speech at the sharpest one.
No.
No, okay, sorry.
Hi, my name is Patrick. I did a certificate in data analytics at Varsity University. I just finished it last month. And I start learning deep learning. So I started reading some books and doing some tutorial tools.
My name is Shad. I work with a local software development company and just curious about machine learning, so I've started some very initial kind of basics around that. Just here to learn more.
Great. My name is Ayajan. Currently, I'm trying to start a now. See how that goes. But this is actually a marketplace of pre-trained machine learning models. I'll tell you more later, maybe. And yeah, I'm just really passionate and excited about deep learning and reinforcement learning.
Awesome. My name is Prakash. I went to and I'm a machine learning engineer at Canvas Analytics right now. And I think reinforcement learning is actually very, very, I think there's a lot in the future. And it also is very applicable to the work that I'm doing. It's something that I need to learn. And very grateful for the organization to get up there. Yeah.
My name is Xiang. I work here at Mongo. I'm as a engineer. Reinforcement. I've been trying to pick it up myself, trying to read Sutton's book, but it's just so damn hard. So this is probably like I don't know, like I don't know how many times do I need to go through this until I can make it usable for myself. So let's see.
Sorry if interrupting, but can we like make a microphone a bit louder? Or is your
Can we make the mic louder?
I'm sorry, like
yeah, Xiang, you were good just now, but before we had two mics open. Like for you guys in your room, we're gonna get feedback and crosstalk. So like you guys at Wrangle just have one microphone open at a time.
All right, I see. So mine is off.
Do you hear echo now?
Now it's good for me anyways.
Okay.
It's good now?
It looks like it's good, yeah. Because everybody else muted from the screen. Yeah,
all right.
On the screen.
Sorry, Thomas.
Yes, my name is Thomas. I'm the machine learning deep learning for 1 year. I tried to analyze the EEG signal and figure out if the patient got the seizure from epilepsy or NEDC or not. And my lab tried to come up with the reinforcement learning starting this year. So that's why I would like to learn something and figure out if I can apply it into the project or not. Yeah, very nice to meet you today.
My name is Austin. I'm a software developer. Well, the Home Depot now, they just acquired a startup. I got into machine learning, deep learning when I worked at Hydro One as an electrical engineering intern. And my final year, I kind of decided to pivot to software engineering and deep learning as I see a lot of potential in the future. It's kind of what I want to do now. So, yeah.
I work at Canadian Tire Financial Services, like a credit card lending company in Canada. I've been doing modeling with them. Been there for like 5 years. I'm kind of playing on the side of my desk with more interesting machine learning algorithms. And recently they kind of branched off and created a more research team, which is what I'm on now. So we've got some time to explore the field, officially, which is kind of nice. So I'm looking to see what else is out there, potentially just, get to know the field more. I went to the NIPS conference a couple of years running, and that's where I met Jiang. So I'm here.
Perfect.
Hi, I'm Amy. I'm a software developer getting into data science and machine learning. Still fairly new on the deep learning side of things, but figure the only way to learn is to be hands-on. So I decided to check out this group.
Great. Thanks for coming here. I guess we'll go over the online people. We'll start with Brian and go to the right, based on the ranking on your, the way you guys display it on screen. I guess he's not online. But there was, okay, no worries. Then Jake. Jake.
Hey everyone. Yeah, my name is Jake. I am a data scientist. Yes, my newest assignment will be starting a new position with Scotiabank soon.
Oh, nice. Congratulations.
Congratulations.
Thanks, guys.
Okay, I guess we'll go to Kaku. Did I say right? It's you? Okay, I thought you Patrick. Oracle is, who's that? Oracle is.
Wait, who are you referring to?
Yeah, Oracle.
Oh, Oracle.
Hi, can you hear me? So, my name is Ignacio. I work for Oracle Software Engineer on the dungeons of operating systems and getting into machine learning for self-diagnosis and health on operating systems, and pretty new on AI, deep learning. Thank you.
Thank you. Really?
Right. Okay. I'm next. Yeah. So I'm Will. I'm down here in the Niagara region, going to Brock University, final 4th year for computer science, specializing in AI, and that's till June. And then I'm applying for grad school, and that'll be continuing for AI, specializing hopefully in deep learning and neural nets.
Thank you. And one.
It's me.
All right, perfect. I guess that's everyone. So, real quick, how many of you guys have? How deep is your knowledge of reinforcement learning? How good are you at reinforcement learning? Like, who's really competent at reinforcement learning?
Like this define competent.
All right, who's new at new reinforcement learning?
Me, right?
All right.
But, okay, you.
Everyone.
Okay, you probably maybe gauges how many pages have you read about reinforcement learning? How do you?
So then we actually prepare it. So that's what we were thinking.
Mark's in the lobby.
What?
Mark. Okay.
All right, I'll introduce our agenda. So we were kind of expecting that meeting members will be relatively new to reinforcement learning. Today essentially is level up. So we all have some intuition for reinforcement learning, some understanding of it. So we're assuming that most of you guys are competent, comfortable with the math and machine learning in general. So today's agenda is to give you like really deep, more of an intuition of reinforcement learning, some ideas. So we're all on the same page. So today we'll cover MDPs. Okay, so today we'll cover MDPs, the basic of reinforcement learning, which is the state, word, action, what it is, how it works. And then a couple learning algorithms, which are value iteration, policy iteration, and key learning. So there's that. And we actually will have a presentation with me and Xian, when we'll present you the idea. Okay, so with that. Finally, all right, so I guess we can turn the camera on and project the slides, and we'll go start presenting.
Can you? I thought about it. Can you project on your slide on your screen? Because I may still need to edit a little bit, like up behind the scenes.
All right. Then I'll just share my screen. Oh, we just introduced ourselves. Maybe you can introduce yourself real quick.
Sure, yeah. Hi, everyone. Mark Alston, faces I see. I'm a fourth year undergrad student at Ryerson. I'm finishing off this spring to graduate. And participating with TLS and FDR since day one. So I'm really happy to be here and going on my machine learning AI journey.
I always see you post like, yo, join this group.
Yeah,
promoting, appreciate that.
Yeah, I try to, big it up and share.
All right, so.
Okay, that's good. So that I can keep editing things.
My screen?
Yes, I did.
You did?
Somehow it's blocked. Maybe it's a. Here.
I'll do it again. Check out our logo. Yo.
Nice.
Willie, what do you think about the logo?
I like it. Good.
By the way, everyone, like, feel free to provide feedbacks. Jake, what do you think?
Sorry?
Like it.
What was the question?
What do you think about the logo?
How do you like the new logo?
Looks good. You mean the one on the bottom of the date and location? Where this whole thing is the logo?
Oh, just the DLRL. Anyway, okay. So feel free to provide your feedback. If you think it's like too dark, if it's too serious or whatnot, I want to make sure it's like our logo. Like, we will be happy about it.
Yeah. I think it looks good.
All right, good. So I guess
workshops. Did I say workshops? Is it just workshops?
Yeah. I don't know. Like maybe in the future we'll extend it to make it a bit fancier, some more stuff. So Jake, Sian, sorry. Sam, how do you want to do that? We want to record it as well, right? And present.
Record and present. Yes. So I think we're well covered because you're recording this, right?
Yeah.
I'm fixing my. Oh wait. You.
Yeah.
Like, it's on your
you
screen.
Gotta be there, right?
I gotta be where?
Presenting by the screen.
I'm presenting my screen right now. That's me.
But do you want to record your guys? You guys want to
So
record
if you fix
there, right?
if you fix the Hangout on my screen, and then it should be good.
Yeah, I mean we'll be standing there presenting. Someone's going to be flipping slides. How do you?
But
do
we
that?
don't have a.
You just want to do like this.
Let me think. That'll be hard. Maybe probably next time.
That'll be hard. Just go through slides sitting.
You mean you want to record the people standing there?
Yeah, us standing there. Or no?
How do you do this? Yeah, I don't see a way.
YouTube Live, you can do your webcam onto YouTube Live.
Then I have to flip my laptop that way.
Yeah. What do you think?
But I still got to operate on my computer, so.
However,
no wireless mouse around it.
Try with this. I have to hold my Okay.
It's okay. Don't worry then. Don't worry. Then we'll just
Yeah,
project this one.
probably next time if
We'll project
we're
slides
better.
like this, and we'll just go over that. So today we'll try to introduce you the very basics of RL. Me and Xian. If you guys know something, if you want to add something, if you have any questions, feel free to stop us or like ask questions or contribute and add your own thoughts to it.
Sorry, you mean if someone comes up, then if it's temporary, then I can do that. I just don't have a camera that's fixed at the
Yeah,
area.
we'll figure that next
Okay,
time.
we'll figure
So
out.
this is
I'll
the
improvise.
first time we actually have slides presenting. That's why it's a bit unorthodox. Anyway, so let me start with the whole idea of reinforcement learning and why we are so excited about it. Personally, why I'm excited about reinforcement learning. Reinforcement learning, actually, the two technologies that made the most progress in machine learning in general were deep learning, and the coolest papers were about deep learning, powered reinforcement learning. And if you think about it, this field is still relatively new. So the most progress in reinforcement learning is done in academia. So for example, for deep learning, we have a lot of applications already, like translation, Google Maps, searches, you name it. Reinforcement learning, it's really cool, it's really powerful, but we still don't know how to bring it to production, how to make money out of it. It does cool things like games and stuff. Commercialized yet. That's why it's still at its infancy, I'd say, but it has a lot of potential though. So right now, maybe in the whole world, there are a handful of people that are really confident in reinforcement learning. They can do some really cool stuff with it. So if you guys learn reinforcement learning and be really competent, you'll be like a handful in the world that can actually do cool stuff with it. So just some motivation, I guess. Anyway, so having said that, let's start with the reinforcement learning. And these slides, by the way, these slides are on our drives. So if you don't have access to these drives, let me know on Slack and I'll add you. So you have access to the folder with all the files, representations, and everything. And the videos will be also available. Anyway, so what?
Okay, if I just post the link on the channel.
Yeah. Okay. Sure. So so what is the reinforcement is when you have an agent that learns the environment. So the whole idea is the agent has limited exposure to the environment, and it can act upon it by taking some actions, explore it, and then based on that, try to understand, okay, this is what this world is about, and this is how I can act to improve, to achieve my own goals. So the agent takes some actions, the environment provides it with feedback, like some rewards on updated states, and then based on this new state and this reward, the agent then decides what to do next. Take new actions or to do something else. So, so the whole idea for the agent is to maximize its rewards. And by the way, this whole presentation is going to be very casual, just for us to explain here. It's not official, fancy, anytime. We're just trying to keep us on speed. So yeah, so the base of the reinforcement learning, the whole thing is built on a thing called Markov decision processes. So by the way, the Markov is the guy from Russia, and Russians, I don't know if you know that, but Russians, they have interesting last names. It's usually like Volkov, which stands for wolf, or something else. Like their last names are based on objects. And Markov, I'm not sure if it's correct or not, but from Russia, Markov stands for carrot.
That's good to know.
Next time you think about MVPs, try not to think about carrots. So what is Markov decision processes? So it composes of states. In this case, those green parts are states. That's where you're standing. Then the actions. For example, these red arrows are the actions that you can take. And then the slow. So reward is as you transition from one state to another by taking action, you receive some reward. And then after that, and there's also a thing called transition probability. Is what are the probability that you deciding to take this action, you actually transition to that action. So for example, and actually, to me, the whole idea of Markov decision processes and reinforcement learning is like the most philosophical subject ever. Like it actually explains the whole life if you think about it. The whole life you can represent as MDP. So for example, let's say you decided to study, right? You're in this stage, you're like, okay, I'm gonna go and study. So you're in the state right now, and your action is, I'm gonna go study. So what are the chances that once you open your computer, you're actually gonna study? Probably 40% of chance you're gonna go and browse YouTube or like check your Instagram. Maybe 50%. So those are transition probabilities. And these are the states. So me being here and deciding to study, me being here is my state, deciding to study, it's action. What I ended up doing is probability. And me actually studying or me browsing YouTube is another state. So that could be represented. So this is the Markov properties. I actually like these visuals. So in this case we have, this is also MDP. In this case, there is a state of a car. So let's say we start the agent's goal is to actually drive a car. If it drives it too fast, the car breaks. It's overheated. But if you drive it slow, the car cools down. And your goal is to actually drive the car. So you're in the state, and if you drive your cool car in a slow pace, you will transition back. With the 100% probability, if you drive your car slowly, you will end up driving slowly. And your reward will be +1. +1 is like how good it is for you, essentially, your reward. So if you drive your car fast, with 50% probability, you go to the warm state. Or with a 50%, you stay in the cool state, right? But if you drive faster, then you go where you want to go faster. So your reward is +2, not +1. Better than driving it into warm state. It's a new state. Now, if in that state you drive it slowly, with 50% chances, you're going to stay in the warm state. And with 50% chances, you're going to transition to cool state. Do you have any questions right now so far?
I understand. So you're looking at probability of state transition with one, either you stay in the same one or the previous one.
Yes. So for example, in this case, right, the warm, you decided your action is, I'm going to drive slowly. So with the 50% probability, you're going to remain in the warm state.
So then if you're showing just probabilities, actions, and states, when do you get to probability, action, state, and outcome? Is the outcome at every state?
So
or
yeah.
Is the outcome like the destination? Or?
So the outcome, this case, the empty, I'm not quite sure what you mean by the outcome, but here's your state, and you take an action, and then you transition to a new state.
Yeah,
which
so
is
I guess the question is the state the outcome, or is it the end of all states?
No, it's not the end of, it's like one step.
One step.
Yeah.
Okay.
So in that case, you actually define your own transition, your own outcome, like the final state. I'll show you in the next slide.
The concept state here is a little vague, in the sense that you could interpret it in two ways. One is the actual state of the environment. If the actual environment is fully known, like a chess, then you know for sure, like deterministically, these are the things. The other thing is, it could also be like the agent's perceived state, which may or may not be in line with the reality. So, and the part is probably reward. So the reward and state, the reward and the next reward and next state, they together maybe becomes your outcome that you're thinking of.
I see, like, for example, +2 and +2, which is you want it to be something more than what it was doing before to get to the next stage. And there's a 50-50 probability that it will either transition to the next one or revert back to the previous one.
I see. I'll get back to that. Yeah, I'll explain it in a bit more details. That one is the returns, the concept that you're thinking about. Yeah.
Okay.
This is just the idea, just to show you that even the state of a car could be represented in the form of MDP. Like these are the different states. So essentially, you can represent your whole life as MDP. Like anything could be represented as an MDP where a state changes. I just want you to get comfortable with the idea of states, actions, transition probabilities, and rewards. So now the good thing about the MDPs, why it's so powerful, is once you have MDP model, you present your life as an MDP, right? Your everyday static habits. Once you represented your life or your habits as an MDP, you can throw your life. Like no one needs to know about your life. Once they have the MDP model, that's it. It explains everything about you. That's why it says the future is independent of the past given the present. So once you have that MDP model, that's it. That's all you need to know to understand the behavior of that system. So the state captures relevant information from the history. Once state is known, the history can be thrown away. Okay, we're more or less clear on that part. Here's an interesting example given by David Silver. I'll post his lectures. He has like a really good series on reinforcement learning on YouTube. Like, really nice. So this is one of his examples. This is the student Markov chain. So let's say you are taking only 3 classes, class 1, class 2, and class 3, right? So from class 1, you can either transition to class 2 once you've completed that, or you can go browse Facebook. Now, Facebook is addictive, right? So if you remain on Facebook with the probability of 0.9, which is 90%, you will remain on Facebook. You'll end up in that loop. And with 10% chances, you're actually going to go back to class 1. I'm like, okay, let me study for a bit. Now, with 50% probability, you're going to transition to class 2. From there, with 20% chance, you're just going to go to sleep. And with 80% chances, you're actually going to transition to class 3. And from class 3, with the 40% probability, you're going to go to a pub and not study. Or with a 60% chance, you're actually going to complete the class and pass the class, right? Now, but probably with the 20% chance, you're going to have to go back to class 1 because you forgot all about the topic. With 40% chance, you're going to go to class 2 because you remember something from class 1, but you need to go back to class 2. And with 40% probability, you're going to go to the class 3 again. And from the state pass, you're done, you passed. So with 100% chances, like you can go and confidently post it. You earned it. So that's the idea. This is how you can represent the class as an MDP. And in this case, it's a Markov processes, which is a tuple of states and probability passes. I think it's okay. I'll show later. So each one of these passes, let's say from class 1 to the sleep, let's say class 1, class 2, class 3 pass. This is called episodes. Okay, so for example, the first episode is class 1, class 2, class 3 pass and sleep, which is this path. This is called one episode. Let's say class 1, Facebook, class 1, class 2, sleep. This is another episode, right here, and so on. So with the with this tuple, you can kind of explain the episodes.
There's no recovery from sleep, is it? Once you go to sleep at class 2.
By the way, this is the sleep. In this case, it's a terminal state. It's the you fall asleep. Okay, you're done. You're good.
No, in class 2, if you fall asleep, you can't.
No, from class 2, yes. If you go to sleep, you're done. Okay. Yeah. No more school free.
Yeah, think of this as a video game. That's the game over.
Yeah. So this is one example of terminal state. You can have a good, in this case it's neutral. In some case you can have very negative terminal state, you can have positive terminal state. We'll cover it in a bit. So let's talk about the idea of rewards. So as I mentioned earlier, for every transition from one state to another state, you usually get a reward. For example, if you go from class 1 to class 2, just being in the class 1, maybe it's not very pleasant. So every time you went to class 1, you're kind of bored. So the reward is -2. And the class 2 is also very boring. So reward is -2. Class 3 is boring. But if you pass, it's really good. So you get +10. That's your reward. Nice, so you get +1 reward. But it's not like optimal. Suboptimal, but that's what you get. If you're in Facebook, maybe you suffer a little less, but you're still bored, so it's still -1. So those are the concepts of reward. The S is the finite set of states. Like you have finite number of states. The P is the state transition probability, which I explained earlier. R is rewards, and Y is a discount factor. I'll cover the discount. Sorry.
So yeah, so if your time horizon is short, like I said, discount factor.
Yeah.
You could essentially just get stuck in one. You let's say it's a small discount factor. You won't think so far ahead to pass.
Yeah.
You might just end up going to Facebook and
Yeah.
just looking up there.
Yeah. We'll cover that right now. This is actually nicely transition to the second slide, which is return. Perfect question. Discounted reward from time step T. In simpler terms, is each one of us have our own return. Let's say my life is my MDP, right? And let's say I'm that agent who's in this reinforcement learning, and let's say my life is this MDP. So my goal in life is to optimize my rewards, right? So what makes me happy? What are my rewards? Is it money? Is it family, love, or whatnot? So each one of you have your own rewards, right? So for example, let's say my rewards is traveling, right? Money maybe not so much. So for every time I travel, my reward is like +10. So optimal policy for me is to maximize my rewards. So travel more. That's the idea. And let's say, but this is the return GT is this reward. Some rewards might be really nice for me right now. Let's say I get drunk. It's really good now, but let's say I get drunk every day. So in the long term, it's not going to be very optimal policy. So by that, I mean, in my whole life, my goal is to maximize my returns.
Then my question is that at every step, the transition probability from one stage to the next, does it also depend on the reward of the next state?
If you actually act on the environment, yes, right now we just cover the MDPs. Yeah. Go ahead.
Terminal things and GT is basically the discounted time value of all accumulated rewards.
In the future, yeah.
That I understand.
Is that per episode? Is that per episode?
Per episode?
Yes.
Yes. So in the previous case, for example, you can compute the returns for this episode.
This is that. Now the sleep state, coming from class 2 to sleep is not the same sleep as coming from fast to sleep, right? Because these are same sleep state, but they are different sleep in terms of.
So yeah, the sleep is called terminal state. Nothing really happens from there. Think of it as a game, right? Every time you play a game, let's say you die, the game is over. And you play next game, and this is new episodes. So there must be a terminal state.
So
go ahead.
Okay. So can you go back to the next one? Oh, sorry. Yeah, this one. This there's an infinity, right? But there's another formulation where you have like finite number of tests. In that case, the infinity is just a T, like capital T. At least in the notation in Sutton's book. So you can either have this or have that. Yeah.
You finite or just infinite?
I think the question I was trying to get to was that the path you took to get to sleep, whether it came from this path versus this path, these are not the same end states, although they are still terminal states. But
I see. I think the question that you have right now will be addressed with the learning policies.
Okay.
Like value iteration, policy iteration, key learning. Okay. We'll cover them right now in a bit. So right now I'm just trying to get you comfortable with the idea of MDPs, what MDPs are and what the returns are.
Just one question. So when you said infinity for the sum, is that when there is a case where there is no terminal state?
Yeah.
That's why it's infinity?
Stay on Facebook.
Yeah.
Just keep doing.
Or like, is this like depending on the object we have different worlds or
worlds?
Yeah, reward. Yes.
Oh, rewards.
Yeah.
Yes. So it's actually very interesting. One of the main challenges in reinforcement learning is to find proper rewards.
Oh.
So in this case, MDP, for example, the rewards are given by the nature. Like let's say if you are modeling the students' success rate, or like how they behave in the classroom, it's defined by students and by the environment. But let's say you build your own game, or let's say you build an agent, and you want it to behave a certain way. So then you have to tune those rewards functions for them, and that one is actually the whole field of study on its own. Okay, so in this case, this is just the idea of returns. And given the MDP, you can actually calculate just one number for returns, because the transition probability, you'll define your discount factor, and then you can compute the whole return for the MDP.
Like an expected
just
return.
one number. Yeah, expected return. So state value. Oh, so another idea here is also as you can see these red numbers inside of states. This is the value of being in that state. So if I'm in this state, what would be the expected return starting from that state overall? If I do the math, well, I guess it will click a little bit more once we go to the policy iteration, value iteration. But this is just so you know, the values inside of those states are called the value for that state.
So okay. The interesting thing, how the distribution would look like.
Yeah.
Yeah, I just want to interject and say that this is, at least for me, okay, if you can get this right in one go, good for you. But yeah, I get an idea of what this is, but we'll go through that. If it's just like my point is, don't be discouraged. If one go doesn't work for you, just keep trying.
Don't be hard on yourself. If you have any questions, our goal today is to give you intuition. So next time when you read it, it's like, oh, I see, that's what they meant. So, and this is where the idea of the policy goes. So if I'm in the specific state, what would be the best policy? So what would be the how I should behave in this environment to, let's say, maximize my rewards, maximize my returns? So the policy is, if I'm in this state, what should I do? You should do this. Okay, once I transition, oh, you know what? I wanted to study, but instead of studying, I went to YouTube state. I'm in YouTube state, I'm browsing it. Okay, what should I do from this stage? What's the optimal action from here? And so on. You should take that will actually make your life better, which is maximize your returns. All right, so this is where we come to reinforcement. Yeah, we'll cover that. Sorry, I didn't want to confuse you right now too much, but the red,
we'll have slides. We'll have slides.
Red lines, if you want to explain with the policies. So this is where we come back to the idea of reinforcement learning. Reinforcement learning is the agent that represents the whole world as a MDP, and then learns how to act upon it. That's the idea. And for an agent, its goal is to find a policy, which is a policy at the bottom P, that maximizes its rewards. And you define those rewards. You define to the agent. Your reward is to collect all the cookies in the game. Your reward is to pass the game. Your reward is
when we are using all the Markov decision process, we are using it to define what is reinforcement learning. Now, it's possible to have something that we would call reinforcement learning that is not expressible by Markov decision processes, is something different. I mean, in the non-formal definition of what is reinforcement learning that I understood before, I see the Markov decision process as a tool that we are using for it, but not necessarily you should be able to describe that using the Markov decision process. If you're doing a simulation, for example, evolutive genetic algorithm, thing to maximize the word function, and in any moment you're trying to get to the complexities of trying to formalize completely the behavior, right? Would that be called reinforcement learning? For example, genetic algorithm.
I think there's.
So honestly, I don't know. All the reinforcement learning that I studied was based on MDPs. Yeah, but maybe there is some. I don't know.
I think the short answer is, I guess the vast majority of the situations can be covered by MDP or some variant of the MDP. You have, what was it like? MDP has this assumption where state and action are fixed, but you could have something they call like a non-stationary situation. And then there's this what is it called, MDP or something, that variant of it that covers more situation. But I think one way or another, what I found is you can formulate your, so it's general enough.
So your slide.
Oh, okay. Let me. Can I move this slide? Oh, okay, I'll just rely on you to move the
I do
slides.
have one question about the previous thing. So if we could, let's say we have all the different possible episodes, the different paths we can take, and we can calculate the GFT of those episodes. Doesn't it just become simply a decision of whichever gives us the greatest reward of taking that path right away? Where does the reinforcement learning come in that?
Great question. I think that's what we'll cover right now. Because what you're talking about is the exploration. That's what you just covered, exploration phase. But there is a phase called exploitation rate that we'll cover in a second.
Okay.
And how you.
Sorry, I missed your question, but.
I guess if this explains, if I still don't understand, I'll ask again.
Okay, yeah, please ask again. Okay, I think it's easier if it's put my, because I have to go like. Actually recording my screen because I'm a little worried if.
I can see
it. If you open, okay, how many of you are aware of Richard? It's called, his first name is Richard Sutton's book on reinforcement learning. Okay, for those who haven't aware, like Sutton's book, as Ayajan's word, is the holy grail of reinforcement learning, because this one single Canadian individual has contributed so much that he just like he's a very prominent figure in the field, and he wrote his textbook is kind of like the definitive guide, and all other variants is more or less like trying to make his things more understandable in a way, and or the more recent advances. His book is freely available online, and it's not easiest but there's it's plain language if you have patience. Like he's one of the guys, probably old school guys, who has very, very long sentences. They just have to like keep reading it, but it's understandable. It's plain English, but you just have to have a lot of patience. A lot of things do not understand and do not click until we reach the end, the last section of the chapter. So that was my experience. So his book has a comprehensive review of pretty much all the variants of different reinforcement learning algorithms. It's impossible for us to cover everything, and then I guess we just picked a few. It's not even typical. Okay, Q-learning, you probably heard of it from like deep Q-learning from various sources, and there's the other very popular one called policy gradient. And then there's the policy iteration and value iteration. The distinction So this group and this group is that the group on the top is also in Sutherland's book called, I think it's called, he calls like tabular methods. So it implies that the agent or whatever, or us coding the environment is aware of the entire state space and action space of the environment, and we are fully knowledgeable about the reward. So the simplest case is probably chess, or something where everything is deterministic, and you know very well if I am in this situation and if I take this action, what's the outcome is going to be. So in that case, if your space is manageable in the sense that number one, you know it, number two is not, it's like it doesn't blow up like to the point where like computers cannot handle it, then this group is viable. And it can, I think it can actually give you a solution. So if you just keep iterating on it hard enough, so it's these both of them have both theoretical guarantees. This is the exciting part. This is kind of like more applicable to real life, where if you can only explore the environment through trial and error. So it's like a animal going like baby going out of the world and trying things out and maybe get hurt or get a reward. And then you have what you have here, in here is a record of things. So that's the yes. Policy iteration?
Yes, because like we already have the yes and no, we can build a decision tree and we can come up with the machine learning model for that.
Yes, the decision tree. Is this yes or no? I think there's some similarity.
Can you explain policy and values? Kind of.
Okay, I have math for that, which is gonna come next. So we had a high. Here's the math, and I wrote this sentence in here because I'm sorry, but because Ayajan told me about it, he's like, let's explain more of the intuition. Then I was trying, but I still haven't figured out a way to get around these formulas, like in order for you to get an understanding. Like I can give you to the best of my knowledge, like the intuition behind all these things, but I guess when to some concrete terms, it keeps coming back at these things. So I think there's some level of abstraction where it just goes to a point where it's not describable in language sometimes. So I'm still trying. If you there's got to be a better way. So if you guys please also, if you had a aha moment and you realize what this is, you have a better explanation, please feel free to do it. And also I'm learning this myself. So this leads to actually a blog post that I found. It's excellent, so I'm going to share it right now on Slack. Also, there's this link here. So I'd encourage you to open this, and because I don't have much in the slide, because I found this blog post, and everything's copied from this blog post. I think this blog post is pretty much what we need. Like it pretty much has go through this without reading through it, but if you get stuck or something and there's text that explains for you, so I think that's probably a better format for you.
I think it would be good too to link the TDLS episode on Q-learning for solving
deep Q-learning
games. Yeah.
Deep Q. Yes. Okay.
That was a good one.
Okay. Can you find it? Yes. I think Arjun is gonna go back to Q-learning.
Yeah, I'll cover Q-learning in a second.
So we talk about MDP. Oh, the other good thing about this is that there's code. I know there's a lot of software engineers here, so code is another aspect for us to understand this a lot better, because code is more or less deterministic. So okay, so Ayajan talk about MDP. So I think I'm not going to repeat here unless there's some. So I think all the notation is the same. You have state. It's nice that. state transition is given, you're probably going to come across this a lot, so it's worth explaining. So given the current state at time t and current action at time t, what's the probability of my next state? In a lot of these, what I find is in a lot of these, I mean, in either code or somewhere else, a lot of times if your environment is fully deterministic, in a lot of cases, it is. So this is automatic equal to 1. So sometimes you see the explicit form of this, sometimes it's just a 1, and they don't bother to write it down. So I think it's you might encounter something and just keep that in mind so that you don't get confused. So the reward is similar. I think someone asked about how is reward determined just now.
I'm just like thinking out loud, right? Just
Yeah.
So when you were mentioning about the probability of the next state, given current state, even though like in the previous slides, the transition probabilities are kind of already given, I'm like thinking, so this might be like a Bayesian like a mechanism. So those transition probabilities are probably like the priors, but then when you're actually on that state, it's like, you know, the like you actually update the posterior based on like this one.
Maybe, but this is more or less okay. This more or less comes from the environment. So the assumption is that if your environment is stationary, these things don't change. Your posterior, okay. So I think it's worth also mentioning on a higher level that there is this distinction between the agent and the environment. So these things all more or less come from the as all the V and Q things you asked about, those are actually the agent's internal reasoning in a way. So yeah.
If I can add something, with the transition probabilities, the reason we care about them is, imagine you have a robot that learns how to drive, and the robot can say, okay, here's the wall, here's the fire pit, I need to move this way, right? So that would be its decision, its action. From this state, I'm gonna take this action, I'm gonna move this way. But because it's physics, because it's real world, not always exactly same thing happens. Maybe it's and it falls in the fire. Maybe it tried to go one way, but it happened to go to the other way. So as internally the robot decides which way to go, it has to account for those transition probabilities. It has to know like, okay, I can go this way, and I'll go to my end destinations faster, but there's a fire pit. And there's a 10% chances that I'm gonna fall to it. So I'd rather take longer route, but I'll be safer. And in the long run, I will maximize my rewards. So that's what we kind of care about, the transition probabilities. Okay, go ahead.
Okay, yeah, just to add on, another example is like if you have a slippery floor and things becomes very unpredictable, like you could end up any other like if you're trying to move forward, you could be tilted toward the left or toward the right. So that's another example.
Yeah.
So it's just taking into account. So similarly, probably the reward. So discount factor, gamma is something that I guess you as the it's a lot of times is a hyperparameter. Do you all know what a hyperparameter is?
It's basically a tunable hyperparameter.
Tunable. I think some cases learnable, but I'm not sure. Yeah, tunable or learnable. So it's something you decide as the robot programmer. So then there's the policy. You were asking about like what are policies. A policy is really sure. In here, it's really a map, a function. So given the current state, what my next action is a policy. But in here, it's deterministic policy. And you can also have probabilistic policy, which is given my current state. And in here, you have a blow up of all the possible actions you can. So that's another way. I think in this blog post, they just don't want to go that complicated. But you probably see that a lot. Like the reason you want to have probabilistic policy is because a lot of times you want to be ambiguous. Like maybe there are two equal, like more or less equally good options. You don't want to like favor too much one option over the other. I think that's
like
one.
chess game, you make the same move every time. Opponent's going to beat you. You'll learn by doing that.
Okay, okay, maybe that, yeah, something. Yeah, exactly. Actually, it's just like in order for you, because in some cases, if you have probabilistic policies, you're more flexible. And sometimes I go here, sometimes I go there, and then I guess the expected overall accumulated chance is that you win more. Anyway, yeah, I think that's exactly it.
The reason you might want to have multiple options. So say you've got two actions that are both kind of like equally good. You might want to have them both occasionally chosen. And for one like specific example, if you're playing a game against an opponent, if you're doing the exact same action every time, they're going to learn to manipulate that. They're going to take advantage of you. Versus if you had something that explored all possible things that were equally good, you're a more resilient solution. Kind of instead of a local minimum, you found kind of exploring all the minimums.
It's interesting about that environment though is then nothing will be static because you get a reward for a certain action, but because you keep doing an action, eventually your reward decreases. Then it leads to like,
I guess it's mental training too.
Yeah, it's interesting.
So the reason I brought that up is because you might see a lot of confusion in notation, because sometimes you see this used as a, like, the value of this is an action, which is kind of like a discrete thing. But a lot of times you see in the formulation is something times that case that indicates that it's a probability. So it's well, when we see that, then that's because sometimes it can be a probability, sometimes it can be an action. So we talk about deterministic environment, like we just talked about it. There's uncertainty about the action and effects. Total reward. Remember, is total reward the discounted reward, or is the same thing?
In this case, is the returns you're talking about.
The discount, the expected return.
Yeah, the total.
Oh, total reward. Okay, it's just accumulation of all the rewards across time. And then here is the formulation we talk about, discounted total reward. But it's not exactly G because it starts at time 1, whereas your G of T starts at time T. I found that the other reason why you do want to do discounts is that the intuitions like future, the more distant future may not matter as much. Another reason is because you don't want this value to blow up. If your game is like many steps. That's the two reasons. Yeah.
So another example that I've heard, which might give you a little bit more of intuition. So think of rewards. Think if you were to live forever, you never die. Would you care about becoming a millionaire? Because to you, you would accumulate the same number of rewards, which is infinite. It doesn't matter if you accumulate infinite number of rewards by $100 a day or $1 million a day. So to you, it doesn't matter. That's why if you want an agent to learn, life cycle has to be limited and your work has to be discounted. And it's actually proven mathematically as well, which is a beautiful formula. Check it out later. Go ahead.
Okay, then this is a repeat of my point, which is we talk about value iteration and policy iteration being a agent like planning, doing offline things, like plan offline, because it can reason within its head entirely, like what the outcome will be. Like what if I do this and what if I do that, and it just reason, like think through about it and derive a optimal policy and goes online and take on the world. So now this comes to our, I guess, the first new thing here, which is value function. Value function. Oh, you talk about value function again. So again, to emphasize, value function is not the actual does not actually come from the environment anymore. It's something that what the agent think how things are going to look like. And this is the part, because if the agent, we're trying to do learning, right? So what do you exactly learn? So this is one of the parts that the agent learns. So the value of this keeps changing as either more information comes in or as the agent goes through more iterations. These are things that keeps updating. So this is the, do you call it parameter? Yeah, this is, I guess, the parameter you can learn.
So in this case, as you can see, V sub pi, it means the value of that state given that policy. There could be different policies and different values for the same state. So as the value of that state given that policy is essentially the discounted sum of rewards from that state, expected sum of rewards from that state. So that E stands for expected sum of rewards.
I thought the states should be a sequence too, right? But here it's just like one state.
Yes, because that value is for that particular state.
So, but then the sum is from 1 to t, from beginning to end, right? So for say, then you're like, I get to a middle state, then like at this state, I am summing from my previous to my later.
So think of it as you go to that new state.
Yeah.
There is a policy for that state. What you should do, state you act based on that policy. You listen to that policy, right? All the time.
Yeah.
If you were to listen to that policy all the time, how much reward do you expect to accumulate from that state?
From that state on.
Yes.
But just not like from previous, because I is from 1, right?
I is from 1. In this case, I'm not quite sure. I haven't read this blog post.
The way I kind of conceptualize it is if that for all states, an element of like the whole set of states, if you're dropped in one state, what is the expected reward total?
Yeah.
And then if you're dropped in that state, given this policy, what would your expected reward be? It's almost like depending on where you started, this is your end result. That's kind of the way I see this. What I was trying to say.
Okay, I think I need to look it up and answer your question.
No, it is exactly that though.
Yeah.
So yes, the value in the state onward.
It's the policy that will determine like the course of actions you take, given that you're in this state,
regardless how you got there.
Yeah.
And you'd also
okay. So okay, you're right.
And
so
you would also see how it radiates outwards, and I'll pull up the image. But that value actually decays. So let's say your terminal state, the final state is like say +1. The very initial value is going to be a lot less than that, and the reason for that is there's transition probability. I'm not sure if you actually going to hold that.
Just back to that post.
To the post.
What is that? The last notation? What is that?
For all states belonging to the state space.
This one?
Yeah.
This means, okay, this is basically saying this is a variable.
Yes.
And what are the values? Some of the values can take is from the entire set of the states. If you are in chess, you can take. If you are in
S.
big S,
Okay.
Yeah.
And the inverted A?
Sorry?
For all.
For all. This is for all.
Is gamma a random variable or a deterministic value?
It depends on, in here, it's a hyperparameter. It's something you did
So it's a
decide.
deterministic scale.
Yeah.
So it's summing. No, I think there has to be a random variable inside because there's an expectation outside. Because we have to take an expectation on a random variable.
Oh, you're saying where is the random variable, right?
Yeah.
The random variable is actually
Could be. Like you don't know ahead of time how many steps they're gonna end up.
but that's not it. The random variable is this. It's implicit. It's buried somewhere in the expectation. I think that's the short answer. There's something you vary, but that's the question I've been trying to figure out myself. But something is varying. If you go through the whole update, maybe it will become clearer if you like start looking at algorithms.
Well,
but that's a good question.
Because given some state and you have some end condition, if we think back to the student example, it's technically an infinite number of paths you could take. But as you get to really long paths, the probability goes to 0. But like each one of those possible paths you take have a different key. And we're basically looking at, based on the probabilities of every possible path, what is the expected value, like given them all. I don't really think it has to be like something, anything random. Like your tech, well, there technically is only we're just summing them all to get expected value.
So you're saying okay.
You share technology too, so we're not
sure.
Exactly, right? Yeah.
So for say if you're staying here, right, and then the one is when we're up to the stage S, there are
Share your screen. Sorry, like
different paths to come here, right? And then it could also go this, and this. This is what you say the T varies, right?
Well, like if say there's like a terminal point.
You share my screen?
I may have. I'm not Hangout.
You should be on Hangout. It should be some of your slides. I mean,
I can't find my Hangout now. Wait, I'm still sharing my screen. So where's my Hangout? Oh, here.
Essentially, like
no, this is not my Hangout.
that T value is before we got to the final end state, and it's like, okay, what do we win from playing this game? But in theory, like you essentially get caught in a loop, and then you end up taking like 10 steps here and then getting to the end. So every time, for every given state, given some policy, there's going to be a path that we take. That's the policy that the
Okay, let me try to stop sharing.
But T, it's just varies based on which way you went to get to the end. That's what I kind of see. It's not like a fixed thing. Depends on which path you take. Gamma is decided. It's like a discount rate. I just think of it in the finance terms. Like you can think of like an interest.
Or like bringing future value to.
I can't find my Hangout.
Time value of money is.
I don't know where it is.
Think about it.
You should I rejoin?
I think you were.
I can't find my Hangout window.
You are online.
Yeah, I'm online. I know because there's an indicator in here. So now I stopped sharing my screen.
Only browser that you use for that.
One.
Only one.
I can't find the window. That's weird. Yeah, I minimized this window. Is it someone else?
One of them.
One of them? What is this?
I know where combined.
It's not here. It's not this. 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 That's weird. Okay, sorry guys. 5-minute break.
I hope so.
I have to quit Chrome right now. Like re-enter. Okay. Okay, I'm not out.
So yeah,
can you share my screen?
The corporate finance analogy is also is correct.
Yeah,
So
no.
you're taking the discounted future value of all V of S to the present time.
Yeah.
And then you want to see you're trying to maximize the discounted value. You know which one of those has the highest probability of outcome, which will give you the highest reward for V of X. So it says here. I can't really bring it because it is full. So VS is the value in any given state that leads. So any given state has some determined value, and of course gamma is the discount or is the reward. So when you look at the development equation, you have the maximum reward of the state and action, and then S prime is the next state after taking the next action at the current state. So your state, say your state number 1, okay, and then you receive your reward at state 1, and then it says, okay, what's going to be the next state? What's going to be that one? Is it going to be the one I'm at now, or the next one, or another one? Okay? So that's what I get here from the development equation.
Okay, I think.
Oh, you wanna see? Okay, you wanna say something? Okay.
Yeah. How about let's take like 5 minutes break, like officially, right? If you guys need to use washroom or something, because some of us went to get coffee and whatnot. Some of us are. Let's check that. Just 5 minutes break.
Okay.
If you need to use washroom, it's right outside. And then we'll come back. I think we need to like really settle the value, what the value is, how you iterate over values, and what policy is.
Yeah,
Because that would, I think, 5 minutes. Give me 5 minutes. You know, we usually don't have these breaks, but I think today is kind of a bit intensive, so we need this break. Like 5 minutes break.
So I'm gonna break. I'm gonna ask you a question.
Question is good. We usually ask questions so all of us can answer.
Okay.
It's always better.
Okay.
We have full brains.
I'll wait for 5 minutes.
Thanks for the environment. That's where confusion is coming from. Because this environment is deterministic, then if you have some learned policy and say you have the optimal policy, then there is only one path to take to maximize reward.
Yeah.
But if you don't know exactly what's going to happen, given your actions, then that's really the expected value.
Yeah, like that was my question initially before. Like if you can just sit down and calculate the expected reward, cumulative reward for every single set of steps that you could take, you wouldn't have to learn anything.
Exactly. That's the deterministic, and I think it makes sense because chess, when Deep Blue first solved it, it's literally
it was
like,
a decision tree, right? It was just the best step, take that one
it's
step.
really just brute force.
Exactly.
Went through every possible combination, and then it always know the best step to take.
And it didn't really learn anything for Deep Blue in 96. Yeah.
But the distinction here is this R is a result of a specific action.
Yeah.
So this is this path is dependent on the action. So you're saying if we exhaust everything, yes, that's exact. Actually, I think that's what the value iteration and policy iteration does. Except that they do it more clever. It's not like brute force exhaustion. If they use dynamic programming, to do this, and then it's guaranteed to be optimal. Like if you run long enough.
And I feel this is also like per se, it's like in stock investment, right? So like at every price, which is your state, then the next it can go up or down. So that up or down, and then that reward up is just like the how much more profit you can make up, and then down like a loss, right? And then you brought it back. So then the up and down will be the policy, right?
No,
like buying and selling.
No, your actions, your action space.
That's one of my key interests.
Yeah.
Is you have an index. So the S&P 500 is the index. The index is the performance of the entire market. So that's going to be your benchmark. And then you're going to look at stocks that will either perform below, at, or above. And anytime a stock performs above, you want to buy. And anytime it performs below, you want to sell. So the reward is you want to maximize your profit, which is the buy side when it is above the average, and then you want to minimize your losses. So you get rewarded for maximization of profit, but you're not going to get rewarded for any kind of losses that you incur. So you want to sell before the losses are incurred, right? That's one example of reinforcement learning that I've seen using the average. I think I published one of them on TDLS, one of those papers. So they use the S&P 500, and they take a random sample of stocks that comprise the S&P 500, and then they try to see, all right, how well do one of these stocks match the S&P 500?
for performance. Yeah, and people have been doing that and still do that till this day. They still try to use reinforcement learning to outperform the benchmark, which is the average.
So how much money have you made last year?
I made the average.
Okay, cool.
The average.
Did you beat index?
Sorry?
Did you beat index?
Yes.
You did?
S&P 500 index. Yeah. No. But you want to buy the average. So it's very, very difficult to beat the market average. It's near impossible.
But when you say market average, do you mean the index or?
Yes, the index.
The index.
500.
So you beat the index.
Did I beat the index? No.
It's
It's hard. It's really hard.
I know. That's why I was impressed.
Yeah. It's
So you
you
said
can
yes.
beat certain. You can beat other indexes like you can perform against like healthcare.
Yeah.
Healthcare is you can usually beat more volatile indexes.
Even beating an index is like you beat it once, so what? It's all in the long run. Right?
That's right, in the long run, yeah. Some people have, beat the index, the stock average for years, but it doesn't last long.
No.
It doesn't last long. Maybe 5-10 years. But the game is to try and at least beat the average. Right? And if you ever see my Twitter feed, you'll see me posting about all that kind of stuff.
All right.
Yeah, it's a really good, learning is really good for that.
RL is pretty good actually. For I think a lot of these hedge funds they actually use RL in deep learning.
They're using it now,
but they don't really publish this stuff. So that's why no one knows this.
And you know why they don't? Because it's almost impossible to beat the market.
Yeah.
That's why they don't post it. They don't really.
It's their whole competitive advantage, right?
They may outperform certain indexes that have a lot of volatility, like tech index or automotive that have a lot of swings. Yeah, you can beat those, but for the market average, near impossible.
The thing about the market average is, and it's getting increasingly true as we go forward, is a lot of the market is now being decided by algorithms.
Yeah.
Buying and selling.
Yeah.
So whatever policy you learn, the environment you're competing in is also other algorithms that are learning their own policies.
And as they learn more
your
policies,
algorithms,
that's
yeah.
right. And as they learn policies, the market becomes more efficient. So it's even harder to beat the market as algorithms can execute trades like this.
There's algorithms even that look for the presence of other algorithms doing something.
Yep.
Don't even worry what the fundamentals are, what's any kind of technical analysis. Just look for the presence of the informed movers and almost try to like piggyback on other people. It's almost like a battlefield out there.
If you want the opinion of the physicists, they have proof that theoretic proof that it is essentially over the long term it's a random walk.
Yeah.
It's essentially so short term it's all short term.
Any advantage you have?
Beating each other. Yeah.
Yeah, Malcolm books there.
Benjamin Graham.
Random Walk Down Wall Street, right? Facebook. He covers that. Walter Malcolm.
There's no advantage will last forever.
That's what everybody says. Just go with the index. That's the best. Over the long term.
I tell people that use free indexes and you
all
beat
you
every other hedge fund.
Buy
manager on Wall
QQQ.
Street.
Yeah.
And people are like, really?
Yeah, do indexes, get out of the way. Just let it go.
What?
Wait, we want to say something?
Yeah, no, I was just agreeing with you guys there. I know there's Renaissance Tech. Renaissance Technologies is one of like the oldest algorithmic hedge funds thing, and they say that their trades make no sense to human beings.
Yeah.
That's right. That's Jim Simons. His
Okay.
hedge fund, and it is the
Yeah.
most winningest or the biggest computer-generated hedge fund ever. It's like worth $18 billion. All done by software.
Yeah, those are all hardcore guys, all theoretical physicists and everything.
Yeah.
Sorry.
Really smart, super. They used to work for the government, and they just kind of fucking handpicked these PhDs, only PhDs. They go to beat the market. They do it by 15-minute increments. Yeah, they're able to predict a short amount of time in the future to execute a trade. So you're trying to find arbitrage, right? Either go long or you go really, really short. So when he decided, well, let's do it really, really short.
Yeah.
And so if you can predict 5 minutes in the future, if a position moves a lot, especially if there's a lot of volatility, you can make a lot of money, right? Every time it goes up, oh man.
Yeah, I think there's a lot of corruption. Well, there's a lot. They got now dark pools now. The last time I looked into it, there's all these dark pools and trades being done outside public markets. And that's where you can win big because you don't have market efficiency because people don't know.
But it is pretty well known that reinforcement learning, it's like for stocks and finance, it's a partially observable Markov decision process. And using it for like algorithmic trading, I'm not sure how great that'd be because it is mostly like high frequency stuff and it's hard to execute and carry out math and heavily computational stuff in the low latency time that they have. But it may be very good for portfolio management and asset allocation reinforcement learning.
Yeah.
Yes, for that definitely for sure, especially for long term.
So let's learn how to do that.
Trading, we're getting into the realm of like clock cycles these days. Like it's just that's the big. You gotta be as close as possible to the data source and as fast as possible.
Trading is about digging tunnels these days.
Yeah.
Fair enough. So I just want to show you the this example. This is the Greek world where and this is the values for each state. The way you can represent the MPP, like the reinforcement problem. So in this case, 1 is the terminal state, which is the exit. If you hit this state, you exit with the +1 reward. This is a pit, fire pit.
Oops.
If you hit the fire pit, then you die, and your reward is -1. Okay. So, and this is just the maze where you navigate how to move around. Okay. So, for each state, each one of these are the states values. As you can see, they're being discounted. Yeah. And these little arrows are the policies for each state. Okay. So optimally, it's going up and to exit. Now, here's the funny thing. From this state, you can go 1, 2, 3, 4, 5 to get the reward. Or you can go 1, 2, 3, 4 steps to get the reward. But the policy says you gotta move to the left. Why?
The cumulative is greater. You add the steps up.
No. There is a fire pit here. And there's a chances that you can slip to the fire pit. And that's why agent thinks, you know what? I'd rather move a little bit. I'm gonna make a U-turn, but I'll be safe. Because there is no way I can fall to fire pit from this state. But if I were to go from this side, I can fall to fire pit. This is where the transition problem is. Go ahead.
Was there a chance of slipping targets before, or?
Yes, yes. So in this way, and this is the whole idea of the value iteration. The idea is that the agent explores the world. So it acts randomly, it walks around. At the very beginning, agent has no idea where it is. So for example, here is a really cool example that I personally like. The guys at Stanford University, they were playing with reinforcement learning, and they wanted the toy helicopter to learn how to fly. So they built a reinforcement learning agent into this helicopter, and like, okay, learn to fly. The reward function was how high you are off the ground and how long you stay there. That was the reward function, right? Now, the agent learned how to fly a helicopter, but it was flying backwards. And then the scientists were like, that's weird, like why is that the case? So they went to physics department and they're like our and physics like, yeah, it's more efficient. There's no drag. So robots, they learn more efficient way to fly helicopter. We fly that way because we gotta enter it, right? But the agent doesn't care. So think of when you are this reinforcement learning agent, to you the world is like a white canvas. You have no idea what's happening. So first you explore the world. You have to figure out what's happening there. Once you learn the world, once you build this image, which is this map, then you know, okay, my value from this state is 0.74. And this is where I should move, which is I need to move to this state because I get higher value from that state.
And that's the basic theory.
Patient, I guess.
Yeah.
So let me show you how this is being learned. From the very beginning, the values are 0. This is where the agent, this is how it starts. It's white canvas. There's no idea what's happening. And it tries to explore everything. There is no policy for it. And then it's like, okay, this one is 1, this one is -1. And then from that state, every time it actually exits the proper, it makes right decision, these values are, how do you say, propagate back.
Mhm.
And as you can see, because of our discount factor, it's 0.72 in this case. And then next time it hits this state, the values are being radiated outwards. So the agent knows, okay, when I'm in this state, when I go to this state, I'm going to get a higher value, and then I can actually exit, and so on. And these values are propagate outwards. This is how you actually build. This is how you actually learn.
And the numbers we're looking at is the value function, right?
Yes, these are value functions.
The V.
The errors of the policy. Errors of the policy.
Errors of policy. In this case,
Arrow. Yep.
Go ahead.
Arrow is given my value.
Yeah.
And what would be my optimal policy is basically argmax.
Because in our value function is a cumulative from 1 to t, right?
They are.
Okay. And I guess the other policy, what it's trying to do is move to the state that gives you the best expected reward.
Yeah.
So it's always pointing to like the higher number.
Yeah.
The noise, is that the probability of slipping into a state beside you?
Yeah. The noise, what do you mean the noise?
Which noise?
Noise point to.
Yeah, yeah.
Also, it's non-deterministic.
Yeah.
I see.
In deterministic world, the agent would prefer from this state would prefer to go this way.
Yeah, always, yeah, because there's no chance that you can mess up.
I think, however, when you look at the discount in 0.9, it's the sum of all discounted all VS for each individual one going back. So if you're to look at the discount rate going like 0.19, 0.435, 75 to 1, and you far side, then you're trying to get the maximum reward for the, I guess, the lowest discount value, right?
I think what it is
Discounts are fixed.
You only get a reward once when you get to the jackpot. So ideally, you just want to get there as shortest as possible so that it just gets discounted the least amount of times.
The least amount of time. Okay, yeah, that makes sense.
Yeah.
Because a long term doesn't count because it diminishes.
Yes.
But then you don't want to just take the shortest route because of that chance that you end up in the fire.
Yeah.
That's what the interesting thing is.
Another interesting thing, I don't want to like too complicated these things, but I think it's interesting to know. There is a living reward, as you can see here at the bottom, which in this case is 0, right? But you can set the living reward to be -1. Think of it as a robot is in a hot ditch. So every time it takes steps, it's like through the hot. So in that case, for agent, every to go to the end-terminal states faster, even if there's a chance of falling into the fire pit.
Kind of like a labor value or something.
Yeah.
How much should you spend to get there?
Now here's the question for you guys: if I'm here, right, and my living reward is -2, what would be my policy?
Just go to the fire.
Just die right away. Because every time you move, you accumulate -2. If you die right away, you just -1 and off you go. -2, -4, -6,
Yeah.
-8, -7.
The one on the top right is not worth it anymore.
Yeah. So you'd rather just -1 off you go.
So you said the value of the states irradiated out of 1 and -1.
Yes.
So I don't understand why that was. Why
Yes.
did it start from 1? Come outside.
Yeah, so because we have a formula for that, and I think you showed that, and you had it in your slide. Can you show your slide with the? Oh, okay, I think I have it here. It's on the. So where is the value iteration formula for you?
Value iteration.
Yeah, do you have value iteration formula here?
You mean the algorithm?
Yeah.
Next slide.
Next line.
Hmm.
No, this is a Q learning.
This is value iteration. At least. Yeah, this is the value iteration. This is value iteration. But what are you looking for?
Okay, can you show me the blog post?
Determine the max.
Let me see.
Use the bottom of it. Yes.
This?
Yeah, this is not quite what I.
That's another problem. You see 3 sources, 3 have different formula. But I think, are you looking for something?
So
Yeah.
can you go back to sharing my screen?
Mhm. Okay, let's look at yours.
Yeah. So simplified Bellman update, calculate the value. So the way those values are being propagated, right? For that we use Bellman equation. So Bellman equation, what it says is, here's my value at this state, and action, and this is what happened to me. So based on that information, I need to update the value of the state that I'm in. Oh, yes, no, maybe. So let's say you say, okay, here's my state, and this state is, let's say, 50. And then I took a step, and then from then onward, I happen to get 60. That means this state is no longer 50, it has to be 60.
It's right next to the reward, so it's a state that we want to be
Yeah.
in, so it has a higher
Yeah.
value.
So from that state, the actual value that I got from that state was 60. But my current information about this state is 50. So how do I change it? Do I like, oh, okay, you know what, this has happened, I'm going to immediately replace my value? You don't do that. You actually replace it with the discount factor using Bellman equation, which is, okay, I see that my new experience proved me wrong. My current value is, see, it's actually just one example. Previous 50 times I was in this state, the value was actually 50. Maybe something changed, but I'm not going to change it immediately. I'm going to a little bit nudge it. And that defines, that is based on that parameter. Where is that? Bellman equation. Where?
Well, if you look, okay, I have it.
You have it?
Well, if you look it up here, it's not going to be exactly the thing you're looking for.
Max Q.
XO equals max. Yeah, it's the same one, just different letters. Yeah, this one.
Okay.
At the bottom.
This?
The one there, yeah, that one. The Bellman equation there.
So yeah, the idea is there is some parameter that you set as, this is how much I will. Okay. So it's not like something happened once and you're like, okay, this is not what I believe going onward. Yeah. It's like, oh, okay, it seems like I was wrong in the past.
The trust value.
Yes. So let me change it a bit.
Is it like a learning method, like learning rate?
Yeah, so this is how much you trust your new experiences versus your own math.
Learning rate?
Yeah.
Is that learning rate, you know, like how fast they're.
There's no learning rate in these formulations because they are guaranteed to converge. Yeah, actually, that is effectively the gamma in here in the reinforcement learning algorithm. I'm not sure the effect of a discount. If you set it to too high, what's going to happen? So it takes into account all the future states effectively.
If it's too high?
Yeah, if gamma is 1.
Please. So I guess here's the let's say you're racist, like you're really hardcore racist, right? And then you believe that certain people are like really bad. And then you meet one person that is actually good of that race. And you're like, oh, how much you're willing to change your stereotypes in your head? If that value is really high, they're like, you know what, I met one good person, no, they're all good. Or you're like, you know what, I don't believe it ever. I never changed my map. I never changed my perception. So you never change. No matter how many good people of that race you see, you never change your attitude. Or if that value is someone, then change your mindset. That's the idea. If that value just changes how fast you're willing to change your mind.
That's beta?
In that case, that's better. Yeah, how fast? Yeah, how fast you willing to change your mind?
It's not representative. Yes.
Yeah, yeah. So I'm not sure. I have this formula for Q learning because that's.
But Q learning is a different. There's a learning rate gamma over there, right? But that's a parameter for exploitation versus exploration. So it's somewhat different.
Yeah,
from
here
the discount factor.
Here it is. And this is essentially the update rate. Update. Shoot. Get away. How do you hide this guy? Okay, like this. So you see in this case, this is the learn rate, but this is a bit rewritten. So here's the new sample that you get based on your world, which is the reward that you got, and then the maximum value going from then acting optimally. So based on this new sample, how much do you tune up your new value? In that case, is you replace your current Q value with the new information, the new sample, plus what you currently believe in. And that algorithm tune it. This is how you update your worldview, or your map, or your policy.
So you're saying alpha replaces gamma?
No. In this case, sorry, the gamma is discounted rewards for the future, right?
Yes.
So
gamma is still gamma.
Gamma is still gamma. Gamma is about the discounted future of rewards.
Yeah.
How much, for example, in a year. So that's your discount.
Mm-hmm.
And essentially, in this case, for example, if you are an agent and you're sitting here, right? So based on your gamma, how will you discount your rate? You'll either go directly, or you'll go around, or you'll choose the path differently. For example, let's say you are here, right? And let's say you only have 2 time steps to leave. Okay, let's say you're here in this day, right? And you can only take 6 steps or 4 steps. Then you will go this way regardless, right? I think this is a different concept, sorry. I'm mixing the reward and the time steps. But there's also the idea in the reinforcement learning where you only have so many steps to leave. And in that case, you're willing to go through fire pit just to get to the final state. Because if you move around there, you never exit. So you never get the final reward. But is how much I value my future rewards versus how much I value them today.
And this is just like one step, right? Like we're choosing max A, so it's the action that'll the optimal action, and then this.
I feel we're skipping a few steps. So can we?
Yeah, go ahead. Sorry.
Okay, can we figure out, because okay, I'll just keep using this because this has a nice progression from. So we talk about this. We have some questions over this. So what you just saw, the Bellman equation, which is you notice there's a star here. That means optimal. So this is an optimal point. So this is actually a equation. Like you theoretically, like your goal is to solve this equation. This is essentially saying if there's a star, which is essentially Bellman equation, and then what is the star? The star is among all policies, what would be my optimal policy, right? So then similarly, like you can formulate it in another way, which is this is my optimal policy, which is basically among all the policy, what is the best policy so that I can maximize this value. So that's basically, I guess, 2 ways of saying the same thing. Okay, I think each one of them is important, so that's why there's so much. So the Q here, we haven't introduced Q function, right, formally?
No.
We haven't. Okay. So Q function is the distinction between Q and V. Q is called Q function. That's what it's called. And V is called a value function. So when you look at this, value function is dependent on policy. The other one is parameters and S. So what is my value function given? What is the value of this state? So it's dependent on that. Whereas Q, this is a Cartesian product. So it has two parameters. One is the state. Given my current state is what is my Q what is my Q what is it called, Q value if I take some action. So it's depending on two things. The reason you want to formulate in this way, use Q and V jointly to express your value update process.
I just noticed something. If you
Yeah.
go to the V function, you see it's a parameter, it's a function of S, right? But S actually doesn't show up in the right-hand side. Where is S in the right-hand side? Yeah.
There's a lot of, okay.
Huh?
You could think of it as like a vector. So you have 8 states. For every state, there's an associated expected value of that state. It's like a mapping. If you look at the, I think of like a type signature. If you think of like ASCII and stuff.
So then in this case, does S affect gamma or
Okay.
R?
This should be dependent on S first and foremost. Yeah,
right?
it's implicit, right?
Yeah, it's
so
like-
that would make sense.
Just S is kind of saying like where you're.
No S. It's a lot of things not written.
I guess since we have policy in place,
Mhm.
this implies that all the actions done, well, even if I were state, if I take some point to get that state, I'm still going to use the policy, so we don't need.
Can you repeat?
Yeah. Because I was thinking of why we don't have the, we had this patient as what is the reward if I
What is the reward if I were to take this action? This one?
I don't buy it. Should be yeah, this one. So I guess by using that policy, we can.
No.
Or does the policy include that we don't have?
The policy is you should eventually take into account this. I think. Yeah. It's a short answer. So
Can I add something
yeah.
real quick about the queue?
Mhm.
So the queue essentially, like Sean said, it's a pair of state and action. So Q actually stands for quality.
Oh, okay.
Yeah.
Okay, thank you.
Ask what that was.
Yeah, which means if I'm in this state, what's the quality of this particular action? So it's really hard to kind of build the intuition for that queue because it's a bit vague. The policy, it makes sense. Okay, this is how you're supposed to act. The value is this is how much you expect to get rewards if you follow the right policy. But Q is a bit weird value, right? So the way I think of it is, let's say you decide to choose a major for school. And let's say the major that you pick is the action. So you are right here, like, let's say at the admission office, and you're picking your major. Is a major that you're going to pick. So Q value is the value that you can, the total rewards that you can expect based on choosing specific major. So if you're in this state, choosing major to become computer science, right? Like, okay, it's going to be a lot of like negative rewards because I'm going to have a lot of sleepless nights. It's going to be very boring, but I'm going to have stable life making money. Or I'm going to pursue music, right? It's going to be a lot of fun, but it's like a gamble. Will I be successful now? Or I can choose only side and be like, oh, I'm going to play for the rest of my life. I don't know. So this is the idea of Q learning is in that state, taking this action, what I expect afterwards. The interesting part is that Q, the way you count that Q, the way you calculate it, is also depending on the future Q values as well. So once you picked the major computer science, right? From that state, Once you take the first class, okay, which class you're gonna take? I'm gonna take introductory computer science. I'm gonna take that, right? Each one of those actions is also Q value. And then there is a policy, the one that will maximize your value, the highest one. Confuse you? Did I confuse you more? Or did I give you some intuition with Q value?
Yeah.
I feel like you have a...
You must be confused. Otherwise, I'm like, what? You're not confused?
You confused? No, more or less, right? So Q value is a pair, state and action.
In short, you can, so Q and V have a very intertwined relationship. You can derive one from the other, in a way.
Examples where Q led you to a state which had a lower value than one you're in order to get a further along result which is better? Or are they always correlated?
I think it would depend on the discount. That would be the
I
case.
think
right?
I think they're always correlated.
Because if you had a case where, say, your discount rate was always in the next state, that will just give you the max, or something like that. Right?
Yeah, you're right.
But then if that would like kind of affect how we would decide.
I think Q is subject to the same kind of discount that V does. So they're kind of like, the two things very, very closely related to each other.
You can like think back like humans. If someone only thinks short term, then they would just gamble, do drugs, and do that kind of stuff, and then forget about the long term. But someone that thinks long term, okay, I'm gonna not spend all my money now. I'll save money, go through some hard times, a better future. I think it's like the same idea.
Yeah, that's exactly right. That discount factor that we were battling with, how far ahead am I willing to look? So maybe I will foresee some downsides today or like tomorrow for the chance that I'll get the really good future, let's say, in 5 or 10 time steps. That's the discount factor.
So there, Q. This is basically your question. Q and V. The optimal V is effectively like given all my actions at the current state S. What's the maximum?
So then does this?
So they're very closely related to each other.
So does this equation, the max in Q,
Mhm.
the same as the above? Max.
Yeah, exactly. They're equivalent. It's just another way of expressing this effectively link Q and V together.
And the difference is one has policy, this is action.
This V is dependent on S, only the current state. So you can say it's a summary of all the possible actions on the state, roughly speaking. And Q is it refers always to a specific state action pair.
So essentially, essentially they're the same. So if you are in that state and it has a value, that value is derived based on if you're in that state and you act according to the optimal policy, what will be the maximum reward you will accumulate, right? That's the definition of the value of that state. The Q value is exactly the same thing. If I'm in that state, what will be the highest Q that I'll get? So it will point to the same policy essentially. Because the goal is to accumulate the same path of rewards.
Almost in a way, Q is more granular than V. V is the sum of how good am I in this state right now, and Q is goes a bit further, like I'm here, thing. Look, what's my prospect look like? What's my prospect look like here, and here?
Hi, could I interrupt for a second? There's Young. You cut out there. Could you repeat what you just said?
I was saying Q almost like feels like a granular another way of expressing V in the sense that Q V is a summary of how good am I in this state given my current belief, and Q is basically saying, like, takes one step further, is saying I'm in this current state. What if I take this action? And what's my prospect? How does it look like for me? And what if I take another action? How does it look like for me?
So is that what this diagram is saying? Each action and there's a value associated with it.
I'm not sure.
I'll show. I'll explain more in a bit.
Okay.
But the idea with the Q-learning, why we prefer to use Q-learning, why we like to learn with the Q is because you can actually learn actively with Q. For example, with the values, you have to test all different policies first before you can derive what the value of this state, right? So you have to know explicitly how the environment looks like, all the transition probabilities, all the rewards, before you can actually compute that value. When it comes to Q-learning, you have the Q-learning for different actions, current belief, right? You took some actions, proved to be wrong. You go to the next highest Q value from that state, from the action to the next highest value. So it's easier to train in life. Go ahead,
This is a quality of a state action, right? Or a set of state actions. Like you're making a quality decision versus just a decision based on an arbitrary number.
Yeah.
Like qualitative, when having a qualitative value, you can then discern. Okay, if I go, then it's one of them.
Yeah.
Yeah. Xian, can you go to presentations? You show me. Okay, sorry.
Okay. Well, yeah. I just want to emphasize one point again. Q keeps changing, just like V, and the V star and pi star and everything star here is the theoretical optimal. That's the distinction. Okay.
I need to show. Is you? All right.
Yeah, the policy slides.
Policy?
It's more like visually easy.
Policy slide?
The one with the squares, right?
Yeah.
The one with squares? Okay, give me a second.
Oh, not the square.
This, right?
Is it that one?
No. The policy slide where there is a Facebook.
Oh, I see. Got it.
It's not easy to understand.
All right. Okay. So it's actually okay. This is actually good. We're kind of jumping to the end, but in this case, the Q values is think you are in this state, right?
Yeah.
In the Facebook state. So the Q value of remaining in the Facebook state is 5. So it's a different action. Yeah. How much? It's essentially the score of the pair of state and action. So in that case, it's obviously better to quit Facebook. You had a question? Or
No. I'm just saying like if you like to use these slides and it's help to more visualize what.
Oh, I see.
Very easy to understand.
Got it.
Is that a case of the values both being 6 and 6, but the Q being better? So we move the next one.
Yeah. In this case, yes.
Oh, so
this one is like closer to the end of the slides. I have like
okay.
progression, kind of jumping.
Okay. This is okay. Q equals to 5. If I stay playing Facebook, why? How come Q is 5?
Because the reward that you get is -1. Value is 6.
Oh, so it prefers this. Okay.
So
again,
go ahead.
This is V, right?
Yeah.
These are V. Okay.
Did you finish the policy and value iteration, or you have more to cover? Because we kind of bounced to Q-learning now.
Let me think. Policy value iteration. Okay. I guess we have to make a decision because it could take a while to explain, and that could consume the whole chapter thing. However, I do think that Q-learning and policy gradient is actually more
important,
more relevant.
All right. Let me then jump real quick to the Q-learning. How do I make it full screen?
So again, just to remind, like we're kind of like we were jumping between two different realms. The policy and value iteration was the full state and full reward table. But in here, not necessarily the case anymore. So it's just like we're advancing into something that's more of unknown. Like we can only learn from trial and error. So that's what the Q learning is about.
Yeah. So this is where it's actually useful. So the definition of Q learning, in Q learning, we define a function representing discounted future rewards when we perform action A in state S and continue optimally from that point on. So to me, this continue optimally from that point on is like the keyword. So we're assuming that once you take this action, you actually end up there, and you'll be like, how do you say it? There's a word, rational. Okay, so you'll be optimal afterwards. So this is the maximum discount. The sum of discounted reward. So this is the nice representation. S is a state, and you have different possible actions, right, that you can take. And you take specific action, and this green state, in this case, they kind of made it a separate green state, even though it's the same action that you take. But they made a distinction here with the green dot, because there is uncertainty. Maybe you took this action, but you ended up in different states. That's why there is this green dot. We all follow this? Okay.
The green dot, according to the form, represents the discounted future value of S prime.
The green dot?
Yeah, it says the next state. It represents the discounted, the discounted expected future reward of S prime.
No,
where is it?
The green
According to
dot.
this here.
Okay, the green dot in this case is but you may end up in different state. S primes could be different.
Oh, more than one S prime?
Yeah,
because you don't know there's transition probability. You don't know where you're gonna end up.
This is the stochastic case I was talking about.
Yeah, this is the. Are we all clear on this?
S prime can be any state or vector state.
Yeah, so let's say you're in this blue state, right?
Yeah.
You open your browser like I'm gonna study,
yeah.
And your action is I'm gonna study, but you slip to YouTube, or you slip to Instagram, or you actually study. So even though your action was to study, the S prime could be YouTube, Instagram, or actual studying. That's the idea. Okay. So this is the this is what we're just looking at right now, which is the Facebook. Each one has a reward, each one has a state, and so on. But the each action has now also a Q value. So Q in this case is, even though I have a, it's for this pair, Okay, we clear here? Oh, okay. So this is the this is how we compute Q value, and this is what I was saying. Q value is, okay, I'm at this state, and I'm gonna take this action A, given that I have K plus 1 steps left. Okay, and then first, this is equal to the transition probability, which is that green dot. This is the transition probability that I will actually end up in this state, taking action A, okay? And this is the reward that I will observe from state S, taking action A, and ending up in this state S prime, because there are multiple of these S primes. So for this S prime, or for this S prime, for YouTube, or for Instagram, or for actually studying, different S primes, what would be my expected, what would be the reward that I will observe, plus the Q value from that state. And the Q value on that state is the maximum Q value. So if you look at this, here's the good representation, right? It's the exact same grid that we showed earlier with the V, with the values for each state. But now we show it with Q values. Because for each state, let's say you have 4 possible actions, up, down, left, right. So for each state, you have 4 possible actions, and each one of those actions has its own Q value. Okay? So you have since you have 4 possible Q values, let's say you're in this state and you take one step to you take action up and you end up in this state. You're not taking any Q value, you're taking the maximum Q value in that state.
These are a priori. You've already explored that space. And
Yes, yes. And I'll actually show how it's being explored in a second.
Oh yeah, this is after 1,000 episodes.
This is one after 1,000
1,000.
episodes.
You more or less you have trained.
Do you have a question right here? Like this is kind of crucial.
Yeah. So the gray.
Yeah. This is in the middle. This is like it's not a stage. It's a block.
So, but it still has certain.
It has nothing. No, it's a wall. You just
okay. It hit it and you stay here. Is that?
So is that the choice over there? Let's say
that's
the
a
one next
choice.
to the red.
Yeah.
That has the highest.
So I see. So
0.42 is the highest in that block.
Yes. Why?
Where?
Yes. Stay there is the best option. Is that what it is? So what it's saying?
Because if you take action up, there is a slight chance that you're gonna fall into a pit. If you go down, there's a slight chance that you're gonna fall into a pit. So in that case, the best option is just hit on the wall, hoping that by chance you're gonna go to the left or to the right, but there's no way you're gonna go back.
Oh.
Because it probably might be dependent on the direction you go. You're more likely to go this way or this way, but less likely to go that way.
Yeah.
Oh, that noise
Okay.
can't make you go back.
But
yes.
Okay, I have a question. But why going up is worse than going right?
Why going up is worse than going right?
Mm-hmm.
In this case, in my opinion, is the robot never chose to go to the fire pit.
Mm-hmm.
So it only chose to go up, and just so happened that actually fell into fire pit. So you see, the Q values are updated only when you take that action. When you consciously like, okay, you know what, I'm gonna go up. Once it fell once to the fire pit, it never consciously chooses to go to the fire pit.
Well, may converge to the best. This is not necessarily the best Q values.
Yeah, in this case, the robot will be like, you know what, I will never choose to go to the fire pit. I burned myself once, and it was bad, and it was like minus 0.43. I don't want to go to the right, but let me go to the up direction. I took it once and I still fell. And I was like, oh, okay, and I fell multiple times, and it was really painful.
So there's more samples for this.
Yeah, for that, there are more samples.
Oh, I can take it. Oh, okay.
Okay.
That makes sense.
So this is the state of maximum Q. Maximum Q of being in that state S and taking action E prime. You take the highest Q value for that state. So this goes back to our example where I'm gonna choose the major. And this right now, right? I have all these different actions that I can explore. I can choose this major, I can choose that major, I can choose that major. And this Q is, okay, if I were to choose computer science, and from that computer science, I will be acting optimally. I'll take the best majors, I'll take all this, I'll join all these clubs, I'll be studying properly and blah, blah, blah. I'll act optimally. Take the highest value based on that. Going onward. And this is the discount factor as earlier. Like how much I value like delayed reward versus my immediate reward. Yes? All right, cool. So this is the Q value, and this is how we update it. So at the very beginning, what robot does, it just explores the whole world. And maybe I should show the example. I love this example.
You want? Let me mute myself. But if I mute myself.
Speaker down. Speaker down, yeah.
I'm muted.
Speaker?
Yeah.
Oh, yeah, there's no way.
Yeah. I don't think it works that way. I have to mute myself.
Unless we just don't play the sound.
Then
You muted?
I'm muted. Okay.
Hey guys online, can you still hear us?
I can now.
All right, sweet. Okay, cool.
Reward was 1, so our new sample estimate is 1. What we have from 0. Now is the
So he's actually right now he's acting manually. So the blue dot is him, and he's controlling like with his keyboard. He's the one picking actions. Yeah.
So first thing I'm going to do, I'm just going to go up and off to the right. Everything is still 0. We actually did Q-learning updates for each of these state action pairs that we visited, but nothing happened because all stayed 0. Now is the first time that we'll see something change. Once we take the exit action here, the sample estimate of the Q value of the exit action here will be different from 0. The weighting factor here, I think, is 1/2. Yes, so we have alpha equal 1/2. The reward was 1, so our new sample estimate is 1. It was 0 before. We weight 1/2, we end up with 1/2. And go again, north, north, east, east. At this point, we know after taking the action east, assuming it's successful and lands in that the state from which we can exit, we know the sample value will be different from 0 because the reward will be 0, but the best Q value in the state you land in, the max overall Q values in that state is 0.5. And so we'll see an update here and it'll become 0.25. Here we are. How about this one here? Take the exit action. The reward will be 1. That will be the sample estimate because after the 1, the value is 0 at all times. So the sample estimate is 1. That gets averaged with what we have right now, which is 0.5, and we end up with 0.75. So up.
You got that part? I was okay, cool. Yeah.
Up. East. East. We saw an update here. We got 0.12. As we keep acting here, you see these values propagate out and taking on more and more meaningful values. Which are the ones that are getting non-zero values? Only for the state action pairs that we actually visited do things change. Right? For a lot of these states, we've never taken the 3 other actions or even all 4 actions, and the values just remain 0. The reason we have a 0.11 there for the up action is because one time I went up and it had an update there. When you go up, what happens? The reward is 0. You stay in place. But the sample is not just the instantaneous reward. It's also the value of the.
So do you see this being updated? Did you notice? So it became 11 because he bumped up and he stayed at the same cell. And so that Q value was updated based on that action.
The state you land in, the value of the state you landed in is the same state in this case. It at the time had some certain value that was added to it, then averaged with the current 0, and you end up with the 0.11 at the time. Let's take a look at this more closely over here. Let's say over here, I would take the action down. What's going to happen? Take the action down, everything stays 0. It's a sample estimate, which is the reward plus value at the next state is 0. What if we go up from here? Value will go up, right? What if we go off to the right from here? So let's go to the right. Initially, nothing happens. That one updates. Now let's go there again. Now it's going down. And let's keep doing this. So let's keep going here and see what Q-learning does for us.
I want to ask you a question real quick. Why that down action from that state is not negative? Because we clearly observe being in that state is negative. It's bad. Why it's not negative?
The triangle when you go down from this state here.
Yeah. Why that triangle for down action is not negative?
It's not propagated so far. Like if he does it again, it will propagate.
No, you already went a couple times.
State sound 0.
So Why?
No, if he does it again, I think it will change. Let's see.
It will not change.
Because the maximum Q is still 0.
Yeah, because the maximum in this case is still 0.
Maximum is still 0?
Is it the one that's in the previous cell?
The max Q here is 0. And the Q learning Q value is only being updated based on the maximum value of the next state. This? Because this Q value is being updated only based on this Q value. The next state once.
Even when you take the wrong action, it'll still continue the propagation of the.
Yeah. Even if at the very end you end up dying, the previous good values keep propagating. So it's like long-term learning, I guess. Okay.
So negative is still propagated. Why is it not propagated for that 0?
This?
Yeah.
Here?
Yeah.
Because this, the maximum Q value in this state is 0. So this Q learning, a Q value, being in this state and taking action down is the reward plus max Q value of this cell, which is 0. So reward is 0 and the maximum Q value is 0. Together it still remains 0. I think he'll explain it a bit more details. I just want like you to think about it first as well.
Yeah. That's interesting. So like you essentially only get positive reinforcement, but not negative.
Yeah.
Because I guess it's LSTM, so LSTM, which is what they use for like investing reinforcement, right?
Yeah.
LSTM or GRE?
Yeah, well,
What's interesting here is that the value for this action here to go down is still 0. Why is that the case? Going down has a reward of 0. The best value you can get from that next state down here is still 0. That's the estimate for the best value. And so this minus 0.81 doesn't affect the value of that state up from it. All right, so this is one interesting property of Q-learning is that even though, if you look carefully at the values, I started acting rather suboptimally here and going through a lot of these states, taking the same actions I've taken before, these values are still going up. You see these values were still going up even while acting suboptimally because it knows that the optimal value from the next state is actually a high value. And it's using that. It's not using the outcome from this particular run. It's using the value of the next state in its sample estimate, not what happened to be happening in this run. So it can be acting suboptimally and still be learning good things. Let's do this again.
there is another example that by the way, these videos are the ones that I shared on Slack. Like really good. Check them out. Two of them. I want to show like another example really quickly. So this problem is a crawler. So you have this toy crawler, which has like 2 joints, and the reinforcement learning agent has control over these 2 joints, here and here. And the goal is to move this box forward. So every time it moves, every time it moves, it gets positive reward, right? Every time it stays, it's negative reward. So right now, the agent in the bottom, this cell, this square is the values, and the X and Y is the action for the joints, like which ones to move. This one, I'm not sure exactly. This one is maybe this one, and this one is this one. So the combination of them is moving essentially.
I've seen other examples where you force train the model like how to walk. It learns on its own, walk, and just really make things.
Yeah. So in this case, it's exact same state space, but this one is more of a Q learning. It's a Q space, right? Okay, so you can see at the beginning, it's still at the exploration stage. It's exploring, you see? It tries different actions, different rewards, and nothing happens. Now, as you can see, the exploration rate at the bottom. Okay, I'm not gonna move my mouse. So you see the epsilon at the bottom is really high. It's 0.8. That means it's still acting rather randomly. as you start decreasing that epsilon, let's say to 0.1, then it will actually start using the knowledge that it learned in the past to act optimally. And I'll show you in a second. So now, after 1,000 iterations, they learned this agent. They learned this state space, the values and the key learning. And as he will decrease the epsilon value at the bottom, you'll see the blue state quickly converging to optimal state.
That's the exploration state.
Yeah, I'll show it in a second as well. You see, he decreased the epsilon, and it quickly converged to optimal state. But in this case, because it's 0, it converts to suboptimal state. It's not acting randomly. If it was at least 0.1, it would converge to even better policy. It would go a little bit further to the green area, where the policy is even better. So these lectures are amazing. I highly recommend you guys to go through them. You have a question?
Yes. Okay. That the previous example.
Yeah.
It's a sampling process, right? So it's from sampling
Yeah.
impact many times without. Okay, can you go back to the equation?
To the equation.
Yeah, the slide.
The learning or?
Pure learning. Yeah, that one.
Mm-hmm.
So it's doing the sampling and it's updating the queue.
Mm-hmm.
Is it doing that update like the last equation?
Yeah. So this is, let me go to this formula real quick. Can you make it full screen? Is it possible?
Here's where epsilon comes in.
It's okay. It's okay. No worries.
Okay.
Now, how do I make my thing full screen? There you go. Finally. So there are two moments that I want you to really understand. First is Q learning is just a table, a lookup table, right? So at the very beginning, you initialize your Q table as all zeros because you don't know what actions will result in what values, right? So on the y-axis, those are states, and the x-axis, those are actions, right? So at the very beginning, your agent acts randomly, like crazy. It tries everything, and it dies, and it has to die. Like, but otherwise, it would never know that these are the bad actions, the bad states. And sometimes it gets successful. It actually exits and gets positive reward. And based on that, it actually starts propagating those values, as you saw earlier, right? And this is essentially, initially it runs through all those episodes that we saw earlier, sample the world, and then updates the Q values for that state, which is Q for S, A. Okay, so it keeps updating all this space, Q table. And here's the formula essentially: define epsilon, alpha, gamma, blah blah blah, initialize Q table to 0, observe initial state. It could be anywhere, right? And then repeat. Select action A with probability, and this is the epsilon. This is the exploration step. So if your epsilon is high, then you explore. You explore everything. You act randomly. In this case, is with probability epsilon, select random action A. With the probability of 1 minus epsilon, choose the best action based on your values, based on your Q table right now. The one with the highest Q value. Carry out the action A, observe next state and reward, calculate target. So this is, the target is Willie? Willie or who is that? Anyway.
I think it's weird.
Yeah. Observe. So then you calculate Q target, which is the reward plus the maximum Q value of your next state discounted. So this is essentially a difference. This is what you observe. This is your sample. Then you find the Q delta. It's like how different it is from what you have today. So how is your new observation reward is differ from your current understanding of the world, essentially, right? And then just update that. Update this state the way you just moved from the Q value for it accordingly, QSA, and then change state to a new state and return. And repeat until converge, until terminated. So this is the pseudocode. This is the example that I just showed you. Now here comes the idea of exploration versus exploitation. This is the idea of exploration versus exploitation is like, to me, it is very philosophical. I think that's what we should do as it really converts back to your life, right? As a kid, you're supposed to do everything, right? You do music, you do sports, you study, you do math, you read, you try everything. You try, you hate it, you drop it, you try something else. You're supposed to do all this. You're supposed to make all these mistakes as a kid, right? Because otherwise, how would you know what you like, what you don't like? How would you find your hobby? Now, as you what? Exactly. But as you grow old, as you mature, you should start converging. You're like, okay, maybe you still want to do all this crazy stuff. Maybe you still want to pick something up, try it, and drop it. Pick something up, try it, and drop it. But you're already like in your 40s, right? It's time to maximize your rewards. It's time to find what makes you really, really happy in life and keep doing the same thing to maximize that thing. That's the idea. So in this case, at the very beginning, when agent just bored and has no idea what's happening, exploration rate is really high. It just goes randomly, does crazy stuff, keeps dying, or sometimes gets lucky. Good. And the reason you have to do that is because in many worlds, there are two terminal states. Let's say you have a map and one terminal state is plus 10. The other one is plus 1,000. But the one that is plus 1,000 is a bit farther away. How do you find it? You should act randomly for long enough to explore that state in the beginning. Imagine if you found that plus 10 and like, okay, I converged. That's my life goal. It's like bad example I'm gonna give you, but it's like marrying someone from like your first sweetheart from high school. You married the first girlfriend. I'm done. I made it. Maybe it's suboptimal cost. I don't know. Maybe it's always
so that value is actually helping us to get out of finding local maximum to try to get
global. Yes, exactly. So that's the idea of exploration versus exploitation. First, you explore enough. You have to explore the world enough to find how can you maximize the highest reward. How can you get the highest reward? Then based on that, once you get there, then you have to act optimally based on the map that you have. So as you mature, as your agent learns enough, you have to turn down your exploration rate and tune up your exploitation rate. And then you start acting optimally. Now, how do you find that? How do you find that rate of exploration versus exploitation? The very simple one is have flip a coin at the very beginning. Like you try it randomly, but then as you go over, as you live your life, it keeps decaying based on your time steps, based on your lives, right? It's not always the best, but that's what you can do. Another way is to actually use the exploration function. In this case, the idea is in that state, whenever you hit that state, you want to act randomly only if you haven't explored that state enough. If you've been in that state many times and you already explored it enough, then it's better to act optimally in that state. But if this is the first time you got to that state, or like this is your second time there, you might as well keep acting randomly at that state. Because in that case, you will explore the world better. And that's what this formula does here right now. So another interesting derivation of this exploration versus exploitation, again, very philosophical. So you don't be hard on yourself if you think that you're not achieving the best of yourself, because it's impossible and it's proven mathematically. There is no way you can be the best version of yourself, because we only live one life, and we don't have this luxury of like, living and dying, living and dying, living and dying, right? And not only that, even if you had the opportunity to live and die all the time, the world is so complex, the MDP of the world is so complex that there's no way you can actually find that optimal state. Let's say you were born and like, you know what, I'm gonna be happy if I become president. That's my ultimate reward. And you live your life, you never become president. You live it life again. But like, okay, I need to go to this school, I need to do this one, I need to meet these people. You die. Next life, okay, I need to go to this school, this, that. And let's say you live 1,000 lives. And in 1,000 lives, you learn the optimal policy and you became president. Is it the highest reward that you can achieve? Maybe you're supposed to be a musician. You don't know. You have to explore being a president, being a musician, being a movie star, being a computer scientist, and so on. And only then you'd be like, you know what? Nothing makes me happy. I just want to travel. So you can never live optimal life based on reinforcement learning.
Something funny just to add to that. I know on the philosophical side, I know like the same for like you have to have some what we call skin in the game, right? So the more skin you have in the game is the more you can determine that risk reward or is that wasn't optimal, right?
Yeah.
So you go through something, you experience it, it's either going to reward you positively or negatively, and then you determine, okay, well, I won't do that, I'll do something else. But it happens over time.
Yeah.
Right? But the more you do that over time with tiny little pieces of harm, the more what's it called anti-fragile.
Oh, this is that Nassim Taleb, is it?
Yeah, like it's philosophical. I understand what this is and the philosophy behind it, and that to me is like the best explanation that I can come up with is you're trying to be not robust, but you want tiny little pieces of harm so you can find the most optimal reward and stay there. It's going to give you the best extraction out of exploring the entire space as you code it, right? If that makes any.
Yeah, it's interesting. I think, could you share that link after to the general channel so we can all take a look at it?
I recommend that book too.
What? Skin in the game. Okay, I'll take a look at it. So we have about 10 minutes left. Let's cover all the questions that we have. I'm not sure if we can cover the policy grading right now. So sorry.
I don't have slides. I didn't even expect it.
All right, cool.
It's too much.
So all the questions that you have so far, like about everything that we covered, I think we tried to cover a lot. I'm not sure how much of it actually.
I'll let you finish, and I'll probably add.
Do you have any questions?
You must have questions.
The slides are shared on Slack.
Yeah. Online, do we have any questions? Really?
I only have like one question just for the overall, this project. It sounds like this is a meteor one and that people care about this one more. So it sounds like we're going to want to park here longer.
Okay.
For this project. How long were you thinking of making this? 2 months?
So I think it's going to be just like any other project we had. Like we'll pick up a project and then we'll try to explore it, and then like essentially until we finish it or just get tired of it. Because that's what happened. Like with the GANs, we worked on it until we got tired, until we finished it. With the RNNs, we worked on it until we got tired of it. So this is going to be the same idea, but I feel like it's going to be interesting, the topic that we'll pick. So to all the new ones, this is how it works. So after today's session, each one of us will propose a paper on the Slack, like something in the field of reinforcement learning or deep reinforcement learning, something that you guys are really excited about, something that you think is very interesting, something that you want to replicate. And then members just vote, like, okay, I'm interested in this, I'm interested in that. And then we pick one paper with the highest votes and just do that. And then we do the exact same thing, yeah. But what we do is we go through the whole paper. First, we try to understand the math. Just like today, we'll just project the paper and like surgically go through every single formula and make sure we all understand what's happening. And then we try to put in the code. And
I
there's
think we've understood everything.
Yeah, that's what happens usually. Like then we keep going back to that paper, like pulling it up. Like, what's happening? Even though, okay,
The timing will be 3 to 6 Saturdays
Yeah.
every.
Yeah.
Last for the plans, it took us like how long? 4 months.
4 months? No, I was like
3
two and a half. Yeah.
Just 2.5. Not like 4.
But that was our very first. It was like even less organized than today.
Okay.
So that's could be why.
Going forward, though, do you think you, especially as the academia progresses with new ideas,
Yeah.
you eventually come back to GADS
Yeah.
and then look at using the next latest and greatest innovation? Would that be the kind of idea that?
Yeah, so the idea is it's a DLRL, right? So we'll bouncing between deep learning reinforcement learning, deep learning reinforcement learning, and it's always up to you guys. Whatever you vote on, that's what we go with. If you find some, let's say next month there is a new GAN paper that you're all excited about, we just go with that.
Okay, so yeah, it's pretty dynamic then based on what's
Yeah.
happening now.
Yeah.
Yeah. The reason we picked the self-attention guy, right? The reason was because it was the state of the art. And as we started, I mean, new things came out. And like by the time we finished, a little while later, like another breakthrough came out.
Again,
so like two generations. already.
In the span of
It's
2.5
4
months.
So fast.
Brian, do you have questions? Prakesh. I keep butchering your names. I'm really sorry about it.
It's all right. That's all right. It's close enough.
Okay. So any questions about the reinforcement learning, the topic that we covered today?
Question about marketing process. Do you think it's not to learn more about the marketing processes? Or
So Markov decision processes is more of a framework. If you have a really good understanding of how it works, it's not really complex, to be honest. It's like state, action, reward, transition probabilities. It's about it. There are ideas like POMDPs, which is partially observable Markov decision processes. And there are new ideas where they have like two agents. Each one of them have its own MDP, its own representation of the world, but then they interlink. Like whatever I do affects your actions. So your policy is based on my actions as well. It's very interesting. Another very exciting area of reinforcement learning is inverse reinforcement learning. So in that case, you're not learning agent's policy. In that case, you learn the reward policies. In that case, you're trying to find what are rewards that guide your behavior. How can I manipulate you based on rewards? Yeah. To me, that's like really exciting. I think politicians are super happy about it. So essentially, yeah, you just you observe someone's behavior and try to find out what guides him, like what's eternal MDP of that agent, and what its policy, the rewards, and so on, and how you can manipulate. Anyway, so there are like a lot of cool things happening around the reinforcement learning. But I think for the MDPs, once you just understand the concept, as you code, as you write, and there are many algorithms, by the way. We just covered value iteration, policy iteration, Q-learning. There's also TD Lambda, which is the Sutton's baby. It's really interesting. It's more complex, but and then there's Monte Carlo, which is like very, very first reinforcement learning. Like it's a grandfather of RL.
Markov chain Monte Carlo, because I came across it in the paper.
Yeah, that one is like a grandfather of RL.
Yeah, we use this sampling technique. A lot with different pieces. Even the policy gradient. Oh, it's not Markov chain Monte, it's multi-pole sampling.
So for the RL, the other topic that you might want to explore to understand it better would be dynamic programming, because dynamic programming is essentially that's what it's built on.
Can you go back to the slide? Right?
Which one?
To the policy iteration evaluation. We didn't cover this, but now that you mentioned dynamic, next one. All these iterative methods, they are dynamic programming. So you could probably start with like simplest case, and there's like entire proof in the book like why this works. but it's another. But again, this is only works if you are fully aware of the environment.
But I don't think you have to be an expert in MDP or dynamic programming to actually use it. It would be really good if you do. But if you just want to use it and build some cool agents, then as long as you understand the algorithms and have intuition, there are even libraries that came out. I was really excited about libraries. The TensorFlow library for RL, they came out. That's something we might want to explore because it's so new. Like if you know how to use it, you'll be like among the handful in the world that actually competent with that. Anyway, and then there's OpenGym AI, OpenAI Gym. So this is the platform that was built by it was sponsored by Elon Musk, and it's like to promote the RL the world. So there you can code your agents that would solve games essentially. Another thing, there's a deep reinforcement learning course by MIT. The professor's name Lex Friedman. Yo, yeah. So you can actually write your own reinforcement learning agent for self-driving cars, and there's a little game that you can play on the browser. So it's also quite interesting. So
What I thought was cool about the OpenAI Gym, when I was reading that world paper thing, the GitHub, the previous best algorithm was like unpublished. Some guy uploaded something and some funny name to like Cash Billionaire 20 or something. He had the state of the art algorithm to solve that game. And so,
Which one? His dom?
the little car that.
Oh,
It was interesting.
So yeah, I think it's already time. Do you have questions or any suggestions, recommendations, guys online? If you have anything to add.
So for the next session, will we be checking out one of these libraries, OpenAI gyms, or will we start working on it?
So ideally, the next session we should more or less finalize on paper and move towards it. And based on that, we usually explore the libraries, what we need for that as well. Yeah. Yeah. So I guess again, the very first session, like next workshop, would be once we figure out which environment to use, it's trying to set it up. Ideally, we'll try to set it up during the week and then come and like try to troubleshoot and help each other with that. That would be ideal.
Wondering too if it's worth trying to explore doing both PyTorch and TensorFlow.
I'm not sure if PyTorch has a library for reinforcement learning.
Yeah, but it would just mean it's harder, right, to do it.
You have to write from scratch, yeah. So in TensorFlow, I haven't touched it myself yet. I just know it's there, right? They just provide you with agents, like those learning algorithms for you available. So you just tune it, right?
Wait, you mean OpenAI Gym or
The TensorFlow RL.
Provides you.
Yeah, the agent.
Okay, I don't know what TensorFlow provides, but if you say if you have an environment, like if you want to code this thing, you want to code environment, but OpenAI Gym and some other thing could take care of that. And for the rest, it's just about coding an agent that learns. So it's not too far away from just vanilla, like learning the deep learning code.
Yeah.
There's nothing much.
To be fair, yeah, that's as complex as it gets usually. The whole reinforcement learning is like just lookup table, at least now.
Right.
So it's not like deep learning where you have to like use a bunch of blocks. It's relatively new
guess, like,
field.
this can get complicated because I remember the PDLS thing on deep learning for playing the party game.
Mm-hmm.
It all depends on how complicated you want to
That's a
get.
good point. I think in that case, there's an argument for PyTorch because it's easy.
Okay, like whatever you guys decide, as always, like vote. Democracy rules.
Okay.
Whatever you think is the
We
best,
can
that's how
argue
we'll
this
go.
out.
Yeah, or
these
factions.
Then we'll have a fight: TensorFlow versus PyTorch.
I mean,
There's always this fight. There's always this fight.
I haven't chosen a dog in this race yet, but like I've just been hearing that PyTorch is like taking over. Then I hear TensorFlow is good because it can run on TPUs and ASICs that are designed to be reused with TensorFlow.
Yeah.
So,
exploitation versus exploration, right? That's what we.
Yeah, the exploration stage right now. Yeah. All right, I'm gonna wrap up the video then. And if you have any questions, Brian, all right, with me, Prakash.
That's me.
It's you. Sorry. Oracle, these. I'm assuming. Do you have any questions?
No, I don't. Thank you.
All right. All good. All good. How? What the expression? Speak up your mind now or remain. What is that? Yeah, I like that. Anyway. All right, guys. To anyone online, thank you for joining. And we'll see you next time.